Today we're going to start our exploration of sound and perception for our Intro to Music Technology class. We'll begin by exploring some basic concepts from the field of acoustics. We might call this part of the study objective sound, in that we're studying sound as our scientific instruments tell us it actually behaves sort of in the world outside of our skins. Let's start by establishing some basic ideas. What is sound? Well, in a simple sense, sound is an oscillation or vibration of some medium. Most of the time, the medium is air. In that case, the vibration is actually a change in air pressure that travels or propagates from a sound source. So a bit of background. Let's begin by talking about air pressure. Air pressure is pressure in the atmosphere, most directly caused by the weight of atmospheric gases above the measurement position. In other words, wherever you're sitting, there's several miles worth of air weighing down on you, applying a certain amount of pressure to you and everything around you. Air pressure can be measured in a variety of units, including the bar, the standard atmosphere, or the Pascal. Air pressure at a given measurement position in the absence of sound is called the ambient air pressure. Sound is micro oscillations above and below that ambient air pressure. Those changes in air pressure can be caused by a lot of different sources, some intentional, some unintentional. So let's make sure we understand a key concept here. We want to understand the idea of changing air pressure over time. If we were to set up a measurement device that can measure air pressure and log the changes in air pressure over time, and we map that out on an XY graph, we might see a representation such as this. At our measurement position, we can see that we initially started at 0. In other words, the air pressure at the beginning of our time of measurement, where my cursor is on the screen, was exactly at the ambient air pressure. And then we can see over some period, represented on the timeline here, that value went above the ambient air pressure. Then at some later point, it came down back to 0. Then we went into a rarefaction part of the waveform where we went below the ambient air pressure. These periods when we're above the ambient air pressure we call compression. These periods where we're below the ambient air pressure we call rarefaction. So let's talk about some important characteristics of this type of shape that we've mapped out. We call this type of shape that we've mapped a wave. So when these represent sounds, we call these sound waves. And there's a few important characteristics that we want to note. The first is that there's a repetition of this shape. In this case, it's occurring just past the number 6 on our timeline. We would call the duration from the beginning of this shape to its next repetition its period, and that's going to be measured in a unit of time. We can also see a maximum value above the air pressure and a maximum value below. We can measure this value as an amplitude, and we'll find that this has some important corollaries in concepts related to sound intensity and sound power. Though we can't see it from this sound graph, we should also understand that sound waves have a duration. They begin at a point in time and they end at a point in time. So let's talk a little about the period. The period of a sound wave is the time it takes to complete one complete cycle. It's generally going to be measured in units of time, and because we're talking about the frequencies that humans can hear, this will generally be measured in the unit of milliseconds. Frequency is the rate of oscillation per unit of time, so it has a relationship to the period. Frequency is measured in a unit called hertz, which is abbreviated uppercase H, lowercase z. Hertz is equal to cycles per second, sometimes abbreviated CPS. Frequency is related to the period of a waveform by an inverse relationship. In other words, frequency is equal to 1 over the period, where p is the period in seconds. Again, this relationship is inverse. As the period gets shorter, the frequency goes up, or the number representing the frequency gets bigger. As the period gets longer, the frequency goes down. As a couple of examples, a period of 100 milliseconds, or 1/10 of a second, is a frequency of 10 hertz. A period of 1 millisecond is a frequency of 1000 hertz or 1 kilohertz. Note that when we use the abbreviation for hertz, we always capitalize the H. We then follow standard SI practice for any prefixes that we've added to it. In this case, the lowercase k represents 1000 of the unit it's modifying. In this case, 1000 hertz. The amplitude of the waveform is the maximum absolute value above or below the ambient air pressure. A higher amplitude would represent a greater deviation above or below the baseline. Now I want to take a minute and I want to unpack this definition. First, we use the term absolute value. What that means is that we're going to ignore the positive and negative signs on these and simply take the magnitude of the deviation as the amplitude. And because we're taking the maximum absolute value, we focus on the peak and the trough of that waveform when we specify the amplitude for a given waveform. Even though we know that the instantaneous air pressure at any given moment in time is likely some value other than that peak or trough value, other than that exact moment where the waveform reaches that maximum value. But again, we define amplitude as the maximum absolute value. So it's a magnitude, does not take into account positive or negative. Since amplitude is a measure of the change in air pressure, the unit is the same as for air pressure. So when we specify air pressure in the field of acoustics, we commonly use the Pascal as the basic unit for measurement. So the base unit on our y-axis in the previous examples was pascals. Since this measurement is based on pressure, we call such measurements sound pressure level or SPL. In terms of common ranges of amplitude that we might encounter in the real acoustic world, the most quiet sound that human beings can hear are going to be in the range of 0.00002 pascals. That is 20 micropascals of sound pressure level. The loudest moments in a big action film in a movie theater would typically be in the range of 20 pascals, and a very loud concert might get up into the 50 pascal range for short periods of time. By the time we get to 50 pascals, we're reaching the threshold of pain for human beings. Now, one of the things that we want to note about this is that this covers a huge range, from 20 micropascals to 50 pascals. And one of the other things that we find is that our perception of sound pressure level and loudness does not follow a linear scale. In other words, doubling the sound pressure level does not result in human beings perceiving the sound as twice as loud. So one of the ways that we handle this huge range of values while also scaling it in a way that will more accurately reflect human hearing is to use something called the decibel scale. The decibel is a way of scaling the ratio between two values logarithmically. We'll come back to that in a moment, but let's finish out the couple of bullet points here. The decibel is abbreviated lowercase d, uppercase b. The reason for this is deci is the SI prefix, meaning 1/10, and bell is the base unit. We are using as our measurement scale 1/10 of a bell. So we need to use the lowercase d and the uppercase b. In some cases, one of the two values that we're comparing may be a standard reference level, in which case we'll add an indicator after the lowercase d and the uppercase b. So here we see a few examples of that. So the decibel is a way of scaling the ratio between two values logarithmically. Now, by using a logarithmic scale, we more accurately reflect the perception of loudness that human beings experience. It also reduces the range of values that we have to deal with in sound pressure level down to a much more manageable range. For example, in the previous example, when we were talking about the quietest sounds people can hear being in the 20 micropascal range, we would say that that's 0 dB SPL. That 50 pascal range of a very loud concert is approaching 130 dB SPL. In other words, instead of going from 20 micropascals to 50 pascals, we've scaled that over about 130 values, a much more manageable way of dealing with it. And the decibel scale at least more closely follows how human beings perceive sound. Though, as we'll talk about in an upcoming lecture, it's very important to understand that human beings do not accurately hear loudness of sound, that our perception of sound, of loudness, is very different than the overall amplitude and power levels. So here we can see a number of standard reference levels using the decibel as a scaling factor. For this lecture, the top one is probably the one that's most relevant. The value dB/SPL refers to 20 micropascals. What this means is that the dB/SPL scale starts with the quietest sounds. 0 dB/SPL would generally be the quietest sound that human beings could hear under very, very controlled laboratory circumstances. But we can see from some of the other ones that we also use the decibel scale when working with voltage levels, when working with power levels, and when working with digital signal levels. We'll talk more about those areas a little bit later in the course.